We know that when we're asked to solve a polynomial, we're being asked to find out what are the values of x when y is equal to 0. This equation isn't currently set equal to 0, so we can't solve it until it is. Subtracting that 4x from both sides, I get 4x cubed minus 6x squared minus 4x is equal to 0. I know I'm going to need to factor in order to solve, but in order to do that, right away I kind of noticed that all of these numbers are even. Personally, I would divide both sides by 2 to make everything smaller. I now have 2x cubed minus 3x squared minus 2x equals 0. Everything's just going to be a tad bit simpler to work with. I can divide both sides by numerical factors. I can't do that with variables because I would actually lose one of my variable factors. But I do still notice that each of these terms has an x involved. So I'm going to start by factoring out that x. So I have 2x squared minus 3x minus 2 is equal to 0. So using that zero product property that you know from back in Unit 4, you now know that either x equals 0 or 2x squared minus 3x minus 2 equals 0. Well, x equals 0 is simple. That's one of our real solutions. We know x could be equal to 0, so we found one solution. But looking at this next trinomial, I'm like, wait, can I factor that thing? Because if I could, then that would be the easiest way to solve. So I'm thinking, are there two numbers that multiply to make -4 and add to make -3? And I can see that there are. I can see that a -4 and a +1 would accomplish that goal. So I'm going to split the middle term. 2x squared minus 4x plus 1x, or just x, minus 2 equals 0. And I'm going to factor the GCF out of the first two and then the last two. So a 2x comes out here to leave me with an x minus 2. And the only thing I can get out of the last pair is a +1, which leaves me with an x minus 2 as well. So they have a GCF of x minus 2 and a remaining factor of 2x plus 1 equals 0. Well, I'm using the zero product property again. Either x minus 2 equals 0 or 2x plus 1 equals 0. Solving each of these for x, I see that x equals 2, or 2x equals -1, so x equals -1/2. So there are three real solutions, and they are x equals -1/2, 0, or +2. Since this was a cubic in the first place, I know that I'm only looking for three answers. We found three real solutions, so that's all that there is. Taking a look at problem number 2, we're asked to find the real or the imaginary solutions to these two equations. Now, our first instinct in this situation tends to be to just straight up solve for x. And if we were only looking for real solutions, that would be fine. But notice it says real or imaginary. When I'm being asked to entertain both real and imaginary solutions, I always need to see if I can factor, which means I need to get one side equal to 0 first. So I'm going to first add that 54 to both sides. And then I immediately see I can factor out a 2, or I could divide both sides by 2. Either way, let's go ahead and divide both sides by 2, because numerical factors don't change what our solutions are. That leaves me with x cubed plus 27 equals 0. When I see x cubed and I see a perfect cube, I should realize that I'm dealing with the sum or difference of cubes. So this is going to factor into x plus 3, that's going to be my binomial factor, times the trinomial, x squared minus 3x plus 9 set equal to 0. Well, that means, using the zero product property, that either x plus 3 equals 0 or x squared minus 3x plus 9 equals 0. At this point, it's really easy to see that x equals to -3 is going to be one of our real solutions. And you're going to be so glad that you remember I told you that when you use the sum or difference of cubes, that trinomial is always prime, so you're not going to try to factor it. Unless the b value is even, it's usually easier to use the quadratic formula than it is to complete the square, so personally that's what I would do. X equals the opposite of b, which is 3, plus or minus the square root of b squared, which in this case is -3 times -3 or +9, minus 4 times a times c, all divided by 2 times a, which in this case is just 2. So let's simplify into the radical. 4 times 9 is 36, and 9 minus 36 is negative 27. So this is x equals 3 plus or minus the square root of negative 27 all over 2. Taking a look at that, we realize that negative 27 is really 3 parts. Negative 1, which is going to give us an imaginary part of our answer. 9, which is the perfect square that goes into 27. And 3, which is going to stay locked under the radical. So we have one real solution of x equals negative 3. And then we're going to have 2 imaginary solutions, which we can write concisely as 3 plus or minus 3i, because the square root of 9 is 3, root 3, because there's still a 3 trapped under the radical, divided by 2. So those are the 3 solutions, 1 real, 2 imaginary. Looking at the second problem in this section, we see x to the 4th minus 9, and we're really tempted to add 9 to both sides and then try to take roots, but we remember that we miss imaginary roots when we do that, so just looking for real solutions is not enough. So we've got to step back and go, wait, how can I factor this? And we realize that x to the 4th is a perfect square, as is 9, so this is a difference of squares. So this is really x squared minus 3 times x squared plus 3, set equal to 0. Now I can use my zero product property and say x squared minus 3 equals 0, or x squared plus 3 equals 0. Now those are not factorable because although the x squareds can be a perfect square, the 3's are not. So all we can do is solve them by square roots at this point. And we realize since these are each quadratics, I'll find 2 solutions by solving for each of them by solving by square roots, which will give me all of my possible solutions. So we start by adding 3 to both sides, and then we take the square root of each side to get plus or minus the square root of 3. In the other problem, we subtract 3 from both sides, and when we take the square root of each side, we're going to get an imaginary answer. So we're going to have x equals plus or minus I root 3. Notice you have 4 answers, and it was a quartic, so you have the right number of solutions. So we have x equals plus or minus the square root of 3 and plus or minus I times the square root of 3. 2 real and 2 imaginary answers. There's a question here just to make sure you realize what's going on. In the problems above, why is it important to solve by factoring instead of solving by square roots type of approach? And we've sort of already discussed that. When we skip solving by factoring, we find the real solutions but not the imaginary ones. So the key here is that we'll find all of the solutions instead of only the real ones. It's important that we catch all the solutions, so that's why we need to take that approach.